Okay, so what we have here is the epoxy going to be doing all the work here. Well, you saw it fail already with the plate in the previous video. Now you'll see the plate here, but you're also going to see a loose bolt. What presents as a loose bolt. You can't pull it out. So I epoxied this path here, the path that broke the other day, and here's the bolt in epoxy, but not actually. The bolt is not actually hit, in clamp force like that. It's just a wedge in there that's been epoxied. You see part of the gap there, but it's got epoxy in it. Let's go with rotating this over now. Let's rotate this over. I should load it this way, but to show you how great this works in tension. As I do that, as I load this, and make sure you can see it, as I load it down, this plate will run against this nut bolt here, and plus the epoxy there that happened to get on the skin surface, the surface tension of it. It happens to bond, make that bond. We'll be counting as resistance like a strong back across the top. That would not be my intent, but we did see it fail when I turned the plate upside down the other way, when I had the plate down in a tension format that I wanted in. I had the plate down, and we still saw the break. Sure, it's not the epoxy fail, but it's a new fracture. Beautiful, and you guys got to see it. And it went off of the same angle, where it was already fractured, but this time down in the angle. You can see the mirrored symmetry of it. So it looks like we'll might have a round 2 of this as far as epoxying this side, clamping, and let's load it again. But let's put this out here a little bit. Make it out. 3 inches or less. We'll fire the machine up and we'll get it mounted, and you'll observe what happens. And what do you think will happen? What do you guys think will happen if you pause the video and be fair? Don't say, "Oh, I thought that." You got to write down what you think. So pause the video and tell me what you think's going to happen when I load this with the machine. We've already shown, just so you know, cheat sheet wise, we've shown that it doesn't break on this side of the epoxy. The screw is in here, but we know that one screw is loose. That's the other side. So this sat, of data to give you, this sat for about 3 days like that under stress, without the epoxy on it yet. So don't think that. But now this has been epoxied. Will the forces now, because of the help of the epoxy, will this make it bond as one? Will it act like this section here now, and be able to transfer the forces beyond that bolt stresses that were created and over? Remember, the bolt had about this much engagement at the very top, and that caused that stress. That's the point where it's bonding this side to that side. But now we have concrete bonding via epoxy. Now it bridges across everywhere in here, with the exception of fine cracks. Let's go ahead and mount her up. Consider that a cycle. We'll go again. Time I'll 2 inches about. That look, I can know the difference. Okay. So it looks like you're in view. Now let's do it again. I feel like I'm on an angle a little bit with the machine with my driver's stick. That's a heavy cycle. Pretty soon it's just when you best just to drive on top of it. Come on. Don't take it off. rotate it off of this thing. Let's get a little more connection. Okay, you're still an image. Okay. Here we go. So once you use the magic of YouTube and slow down this video to 1/4% also, and watch the transition from the fracture, from the tension to the compressive side. As you can see, the epoxy held up. Did we miss that bolt? We did miss the bolt. The epoxy held up, and we lost it in the concrete, not in the epoxied area. The concrete couldn't take the cycling and the stresses. Let's see here. Looking for cracks. I'm looking at the cracks too to see if any stone split, non-split. I'm pretty happy with this testing. Pretty happy with this. It's there was no epoxy at the base of that, so for fairness, it just appears to be a crumb. Let me turn this over. Right, here we go. Just an insignificant epoxy. Over here, let me zoom in. Over there, we'll take a look at the fractures. And you'll see that the epoxy stayed together, or fracture stayed outside the epoxy zones. Well, it looks like almost like it crossed it there, but it didn't, because there's no epoxy in here. It just happened to fracture right outside the zone. Look at that. There's the epoxy. This is the face of the epoxy. It did fracture on the face of the other side of the epoxy. There's the epoxy right there. Look at it. That's the line of it. So you can see the epoxy was stronger than the bond of the concrete, of the mortar rather, in Portland, which I knew it was anyway. But you guys now know that your epoxy was stronger than the bond of the concrete. That's literally the mapping. The stresses of it just pushed it right to the outside of the epoxy zone. It pushed it out of the epoxy zone right to the edge of it. You see the shape of it? It's right there on the edge. That is beautiful. So we would expect the epoxy to be stronger than the Portland. Make sure the camera shows it. And there's that, remember the mirrored pattern? Mirrored? Well, here's the mirrored pattern here. Not over here. You don't see any concrete, any Portland, any epoxy over here. But you see it right there, a little bit, right on the very edge where it came out. So this is where it developed its full fracture. Beautiful. It's beautiful. Now, if we look at it as, if you guys ask me, where do you place rebar? Well, if you look at this, this has a cup in it. See the cup? And that was a hinge point created by the stresses. And those stresses, if you're looking at a finite element program, should have made it look exactly like this. Of course you can't, because they don't graph it that way yet in programs. But you can see the profile of it. So that's the compressive side, and the tension side is below. The compressive side is above. Tension side is below. Act like a hinge. and it's actually cone shaped, if you will. It's internal, like a cup, a ball, if you can imagine going in there. There's the shape of it again, the profile of it right here. Let's see if I can turn it sideways more. There you go, there's the shape of it. So this is your compressive side and your tension side. And you can see in the middle was the neutral axis. It stayed away, it was neither. And in that case, it was, as per the loading that it was put on it, it was a good ½ inch of neutral axis. And the reinforcement there was probably practically useless. Let's look at it this way. Beautiful. It's beautiful. So here's the way that it was loaded and the way the concrete failed. So it actually was kind of high up, only about 1.25 inches right here, but then it changes its profile on the fracture down to here. So here's my hand. Here, I'm going to follow the pattern. There, and back down. And that's the way that looked, per the loading and the twist, the torque of this failure. And this one, okay, so let's see if I can find you the neutral axis. So I'm going to stand on top, high points, then rotation, and about like that. It's beautiful. Now down here on the compressive side, where it was being pulled apart, the tension side rather, tension side over here, being pulled apart, it looks like that. Watch my thumb go drop. That's the profile of it, per the rotation, the torque, and the way it failed. Alright, hopefully this is some good data to help you understand. It depends about your loading. Someone asked me about, quite often I get asked about, what do you place the rebar? Well, it depends on the loading. And also the slab, obviously what position the slab is in at the time. This one we saw was in a rotated position as the machine climbed on it. You saw it took quite a few cycles before it finally fractured abruptly. Imagine if that fractured abruptly in the butterfly area of this pool deck. That's just going to cause puncturing everywhere and it's just going to pull down everything. But look at that profile again, and you're looking at the moment, and it's down in a shear plane, down in the middle of it. That dissection of it has its own dynamics going on per where the loading was at the time. And you can see the two sides as one side that had the weight on it. Probably be the side to the right, and and let's see, it could be actually either side. I would say it would probably be the side to the right having more of a that's a tough one because of the plate. Alright, so wherever the tire was at time of fracture, yeah, whether it was on the left side, the plated side that you see there, or on the other side, what matters is that's the side the loads were on, and that's how it decided this cone would be shaped like this. On the left side with this, like a C-shaped cone, I mean indented C, if you will, and then the outer, the one to the out in the back there would be the other part of that C. So you can see the stresses. It's beautiful, and you can see the stone. They're about all similar. So, all right, a lot of air entrainment in that concrete. There's some good data, good stuff to learn. I think we may not be done with this. This may get another cycle of epoxy and loading. Although my camera died, but I was saying we should be able to predict now how fractures will happen once you see epoxy. That the epoxy section is your indicator of your crack section. If you see a repair there, you can probably assume that the epoxy won't fail again, but what will fail is next to the epoxy. So the stresses will still be there where your epoxy location is, but now you'll move the failure to the opposite side or to either side of the epoxy zone. and not the epoxy crack itself, there itself. And you also saw that it was an abrupt fracture. There was no stretching, elongation. It just happened. An abrupt fracture, an acute fracture. All right. Take care. We'll see you in the next one. So for you contractors and engineers and general people out there evaluating a structure, if you see epoxy placed in a ceiling, for example, you wouldn't actually look for you would look, but you wouldn't find more than likely that the epoxy has failed. But you know that's where stresses are resolving themselves. So you would then start evaluating this crack. That crack is having existing stresses at that location. Just because you closed it up with epoxy does not mean the problem's fixed. It means it's the stresses were still, well, maybe it was a one-off, somebody put heavy loading there or something happened to cause the crack. But if not, if there's no one-off, then you need to resolve that crack issue.